quasicrystal quanta in geometric series. When I gave this solution to the March meeting 10 years ago, the response was warm, if not hot. Then the issue was structure and diffraction. Now it is quantum and harmony. This presentation divides into three: the probe, second phase crystals, and quasicrystals. And the latter separates into diffraction, structure, quasi-structure factors, analysis, quasi-block waves, and verification. We reverse to the 19th century wave-particle duality with Maxwell's equations, then special relativity, Planck's law, the de Broglie hypothesis, and simplify the units. We find easily that mass squared is equal to omega squared minus k squared, which separates into two functions, a conservative function and a response function. The conservative function is an envelope function which describes the conserved properties, mass, charge, spin, etc. And the response function is a wave function which has the density of 1 for all x and t. This is the wave that scatters off the quasicrystal. In this presentation, we're interested mostly in the quantum of momentum. The incident wave has k vector k, and it scatters elastically to provide a quantum of momentum, which is equal to n, approximately equal to n times 2 pi over d. Here's the crystal. It's phase sharing, it's periodic, it's space filling, and it follows Bragg's law. N lambda equals 2d sine theta. Order n is equal to 0, 1, 2, 3, 4, 5, 6. In this instance, odd orders are suppressed by structure factors owing to the symmetry of the unit cell. This is the second phase in melt-spun aluminium 6 manganese. N is integral, periodic, and harmonic. And you know from Physics 101 that the wavefronts in the crystal arise from harmonic interactions with the periodic atoms. The quasicrystal is altogether different. Here's n, 0, 1, tau, tau squared, tau cubed, tau is irrational. It's aperiodic, it's anharmonic. How in heaven and earth does it diffract? Well, the structure, both the diffraction and the structure itself, are icosahedral. Here's the diagram of the principal axes of the icosahedral structures, and normal to the axes, the diffraction planes. They are all three-dimensional, geometric, simple and complete. The manifold is R4. Well, how do we calculate the diffraction? We can't use Bragg's law because it doesn't apply. We have to use the structure factor method. And for that, we must know the structure. The unit cell contains a manganese atom at the center, which is dense and small, and 12 aluminum atoms closely packed surrounding it. In the solid, the unit cell is edge-sharing, so the stoichiometry is aluminium 6 manganese. Notice that normal to the five-fold axis are 5 atoms of a circle, 2 circles of fine apples. 5 atoms. We're going to see that structure in again. And these unit cells cluster into an icosahedral cluster with a stretching factor 1 in the icosahedral unit cell stretches to tau squared in the icosahedral cluster. And then in the supercluster, tau to the power 4, tau to the power 6, tau to the power 8, the structure is infinitely extensible. Knowing the structures, we can calculate the structure factors. But first we can confirm that structure with this phase contrast optimal defocus image of Bursell and Peng. The image is in reverse contrast. Here's manganese, here's the unit cell. 10 unit cells on 2 circles form a cluster, and 5 clusters in this thin section form a supercluster. Beyond the supercluster, the structure is off-plane. So we know the structure. How do we calculate the structure factor? In the crystal, we project each atom in a unit cell onto a selected plane normal and sum the cosine faces. In the quasicrystal, we make two adjustments. Because we have multiple interplanar spacings, as was evident in the last slide, we include a coherence factor CS. And because our unit cell is now periodically repeating, we have to evaluate the structure factors iteratively over the whole quasicrystal, not just the unit cell. So what's the result? There's no Bragg diffraction. If there were Bragg diffraction, it would occur on the ordinate axis. But when we scan CS away from the Bragg condition, the quasi-Bragg peak pops up on the quasi-Bragg condition. And the first surprise, it pops up at the same position for these four beams we started with. And a much greater surprise, it pops up at the same position for all the beams in the original data in 3 dimensions. It's a universal number, so we call it the metric. And what is CS due to? It's a kind of breathing strain in the quasicrystal, a virtual breathing strain that causes the diffraction to switch on and off as the quasicrystal rocks about the quasi-Bragg condition. We're going to analyze it in detail. You can easily show by mathematical induction this irrational fraction total of the m is equal to this Fibonacci sequence. 1 tau, 1 plus tau, 1 plus 2 tau, 2 plus 3 tau, 3 plus 5 tau equals tau to the power 5, etc. And this divides into 2 Fibonacci sequences, one natural, one irrational. You can approximately rationalize this by substituting for tau 3 halves and separating the natural part from the irrational residue by subtraction from the irrational number. And the metric function then gives you a number which, with the greatest surprise of all, is the exact inverse of the coherence factor that we discovered in the quasi-structure factor. The probability of this happening by chance is so small, we know that we understand CS very well indeed. We can now make some measurements. But first, let's illustrate what CS is. Look at the blue wave. This is a block wave in a crystal. It's commensurate with the unit cell and commensurate with all unit cells periodically repeating, but incommensurate with the quasi-lattice in the hierarchic structure. However, if we stretch the blue wave by the metric function, we find a wave that is commensurate long range on geometric indices and locally short range around each index. So we have a dual harmony. With this, we can do some measurements. The quasi-block wave is translationally invariant, both long range and short range in the quasicrystal. Here's the quasi-Bragg angle. 35 years ago, several of us measured the lattice parameter assuming Bragg's law. I knew Bragg's law was wrong, but it took me some time to correct it. Now we know the quasi-lattice parameter is 2.9 angstroms. Here it is. And it is exactly equal to the diameter of aluminum, verifying both the structure, the diffraction, and the metric. But notice one further feature about this cross-section. The icosahedron has 30 edges and 15 cross-sections identical to this at various orientations. The icosahedra are quasi-spherical. The hierarchy is of densely packed balls, which are uniquely aligned by edge sharing. We can summarize. The quasi-metric harmonizes the irrational space and digitizes the resonance response with dual harmonies. You can compare it to the 12-point equal-tempered chromatic scale in Western music. We can define the quantum. It's a localized conserved properties in a harmonic response function. And we make a further hypothesis. The dynamic quanta are always harmonic, like spherical harmonics in Schrödinger's eigenstates. They're dual in quasicrystals. Math quantas are bare numbers with ugly corners, and I list a few. By contrast, again, physical quanta are beautiful when verified.